On August 26, 2026, the water levels in the Trishuli River Basin rose by 9 meters in just 30 minutes. A thick wall of water, sediment, and boulders tore through the Nepal-Tibet border corridor. It scoured the valley floor and swallowed entire agricultural terraces as it moved downstream. When the floodwaters receded, the cause remained a complete mystery. Early chaotic reports blamed a magnitude 4.4 earthquake, while other agencies pointed to a sudden, localized rainstorm. Figuring out the truth in this kind of extreme, remote terrain is a slow process. Scientists have to parse seismic records, pull satellite imagery through heavy cloud cover, and model water flow just to reconstruct the event. But a village in the direct path of a flash flood does not have days to wait for a peer-reviewed scientific consensus. They have only a few minutes to evacuate. In the modern Himalayas, geological and climate failures are increasingly interconnected, where a single landslide or meltwater surge frequently triggers a secondary chain reaction through the river system. Understanding a disaster and surviving one require two entirely different timelines. This forces us to rethink how we protect vulnerable communities from threats we can't immediately identify. Months of post-event analysis dismantled those initial reports. First, the rainstorm hypothesis fell apart when local rain gauges in the Rasua district showed 0 heavy rainfall before the surge. Then the earthquake theory dissolved. The United States Geological Survey analyzed long-period seismic waves and reclassified the initial signal. There was no tectonic rupture. It was a massive magnitude 5.2 landslide. This cross-section shows the cascade. High near the peak, glacial ice collapsed, triggering an avalanche. The debris slammed into the Lende Kola River, acting as an unstable dam, causing the river to back up. The pressure mounted until the dam burst, releasing a catastrophic wave into populated areas. This transboundary zone is highly volatile. Just 1 year prior, in 2025, a superglacial lake, a pool of meltwater sitting on top of a glacier, burst its banks in this exact same region. Tracking this complex chain reaction is an incredible scientific feat. But to the people living downstream, the specific mechanism causing the flood doesn't matter. They only care about the incoming water. Because we cannot wait for perfect science, engineers have proposed a different approach, a multi-hazard early warning system, or MEHEWS. The philosophy behind this architecture is simple: detect the hazard at the source, confirm it in the river, and issue a warning immediately. On this topological map, source sensors monitor high-risk glacial lakes. Downstream, water level gauges provide undeniable proof of a flood wave. The system escalates from a green state to blue, then amber. Finally, a red evacuation order immediately triggers sirens, prioritizing speed over human confirmation. By separating the initial hazard trigger from the physical reality of the rising river, the system bypasses the need for a scientific diagnosis. It prioritizes actionable lead time over perfect data. Technology only solves half the equation. The most advanced sensors in the world are useless if the exposed communities don't know where to run. The communication network requires layers of redundancy. Planners rely on overlapping methods like FM radio, targeted SMS, and solar-powered outdoor sirens, because a massive flood will likely wipe out cellular towers and power lines. Because these hazards often originate in Tibet and flow into Nepal, upstream data must cross the border instantaneously to save downstream lives. This requires a strict, pre-arranged cross-border operating protocol. On the ground, communities must conduct regular physical drills and follow pre-mapped evacuation routes to designated high-ground assembly areas. The ultimate operational test of this warning chain is brutal. It must function seamlessly at night, during blinding weather, and under complete infrastructure failure. The August 26th Bote Koshi flood gives us a clear lesson. In the face of compounding climate and geological hazards, delaying protective action in the name of scientific certainty is fatal. Modern disaster engineering prioritizes the guaranteed path to safety, ensuring that when the next slope fails, every resident in the valley receives the warning they need to reach high ground and survive.